everyone. My name is Joanie. I work at Simwell. I'm a simulation consultant, and today we're here to present our project with Mitchel Lincoln.
Hello, everyone. I'm Akram. I'm a simulation consultant at Simwell.
Hello, I'm Christian Roy. I'm Vice President Operation and Supply Chain for Mitchel Lincoln, the customer in this case study. We've chose Simwell to be our consultant for helping us with our simulation of our plant in Drummondville.
So we're going to present the project today. I'm going to share my screen. So we chose to name the project Road to 2 billion square feet, and you're quickly going to see why. The project aims to use simulation and specifically a Simio model to find the best investments to bring the theoretical capacity of the plant to 2 billion square feet of production. So quickly, we're going to introduce Simwell and what we do. Then we're going to introduce Mitchel Lincoln, or rather Christian is going to talk about Mitchel Lincoln. Then we're going to talk about the business problem and why we chose to do this project, our analysis approach, the simulation model scope and its capabilities, and a bit of why we chose Simio as the best software to carry this project. And lastly, we're going to talk about results and findings of this whole project. So quickly about Simwell. Simwell is a company that does optimization, simulation, digital twins that are simulation-based, a lot of decision intelligence design and data strategy and integration. In this project, Akram and I were really focused on the simulation side. And more specifically, we did simulation of one of the manufacturing centers of Mitchel Lincoln.
So let me introduce you to Mitchel Lincoln. The company was founded in 1965 by Mitch Garfinkel. It's been a family-owned business since the beginning. It's always been a leader in sustainable packaging and manufacturing technology. We are number one market shareholder in Quebec for Corrugated, which is a market split between big players. We're very proud to be the number one. We have a couple of plants in Quebec, 5 in total. We have 3 in Saint-Laurent, Montreal, 1 in Drummondville, and 1 in Vaudreuil. In total, our plants accumulates 950,000 square feet of manufacturing and warehousing capabilities. Mitchel Lincoln is also part of a broader group, the Atlantic Group, that is fully integrated in packaging solutions. Here is a map of the different locations. So basically, the Atlantic Packaging Group has operation in the United States, mainly in 3 states, Illinois, Ohio, and Pennsylvania. In Quebec, we are under the Mitchel Lincoln name, and in Ontario, where there's the most activities. We have all our paper mills located there, and box plants and other divisions. So in total, there is more than 20 facilities both in Canada and United States. So why did we choose to do simulation for this project? You have to understand that the corrugated business is a market that grows faster than the economy. Reason being mainly these days because of the online shopping. The market used to need 1 box in the past where the manufacturer were sending boxes to a retailer. So there was 1 box for transportation and then the products were put on shelves. If you think about it, nowadays, the manufacturers send their goods to distribution center where they're going to be picked and repackaged to be sent as parcels to homes with the digital online shopping now. So because of that, we've been seeing the growth faster than the economy. Mitchel Lincoln has 2 out of the 4 main box plants that are running at capacity these days, and they are landlocked. So basically, these can't be considered for expansion. but we have one plant in Drummondville that still has room for expansion. And we need to plan it ahead of time because, as I said, the market is growing and there's quite long lead times for doing expansion. So we need to know where we're heading. Everybody has option and thoughts about what we should be doing. Should we change this conveyor? Should we change this transfer car? Should we double it up? Should we add conversion capacity? So everybody has their thoughts, but to really be able to look at all those scenarios, we need something that weigh them out and guides us to figure out which is the best option for the sequence, the capex, and the capacity obtained by each of these scenarios. The product mix is extremely wide in corrugated. If you think about it, we don't have any standard product. Every customer that we have has a different box for every product they make. So there's nothing that is the standard SKU like you're going to see in other businesses. We're going to have so many different products to make with different manufacturing capabilities. So this is the main constraint that brought us to utilize simulation for answering all of those questions.
Thank you, Christian. And we're going to see that this was one of the challenges in our model, but we addressed it specifically. So just a little bit on the high-level process of making paper boxes. So it starts with corrugating. You need to corrugate different sheets of paper together to make it a little bit thick. Then there's usually some material handling to carry those piles of corrugated sheets to the point where they're going to be transformed into boxes. So this can involve cutting, gluing, printing, and bale formation, which basically means stacking the boxes on a pallet or not a pallet, it depends. And then there's packaging, so that involves strapping, putting them on pallets, as I mentioned, and you can wrap them in plastic wrap if that's what the customer requires. And lastly, shipping or storage. So we're going to refer to the corrugator, which is the big machine that corrugates, the train, the garage, and the floor. The train is something that transports piles and mostly piles to a garage and a floor, which are storage spaces. The transformation is done by presses or a laminator, which is a fancy printer. And then palletizers or unitizers are the packaging equipment. And lastly, forklifts are mainly used at shipping. So the business problem. In 2025, Mitchel Lincoln produced 1.4 billion square feet of boxes and corrugated sheets in their plant that we use that we simulated basically in this project. But recently they purchased a new corrugator, and this one has a capacity of 2 billion square feet of production. So we would think that the plant would now be able to produce 2 billion square feet. However, there are bottlenecks more downstream. So the current throughput is still 1.4 approximately billion square feet. The suspected bottlenecks are either the train, at the presses, in the garage, or the packaging lines. So this was really the ultimate goal of the project, to really identify the bottlenecks and even find solutions or test different investment solutions in order to lift those bottlenecks and basically really bring the real capacity of the plant at 2 billion square feet. So why did we use why did we choose Simio to support this simulation project? The first one is because it's really data driven. It's easy to have a lot of data tables and to organize them nicely in the software in order to use them efficiently in the model. As Christian mentioned, the orders are really like customized. We have every order is customized to the customer, so that already means a lot of data, even if we found a way to simplify that and we needed a software that could support large data tables. It allowed us to have a flexible layout. So some scenarios that we're testing involve moving the presses around. So we were able to do that very easily with Simio. It's also modular object-oriented design, so all of the presses and the trains were developed as reusable Simio objects, and then eventually we can just move them around or change the parameters in order to have a new press in the model, and that was really quick, really easy, really efficient. We used a lot the experimentation, the experiment actually tab of Simio, and we could do rapid parameter adjustments and really look at the response variables and their change when we would change scenarios. We use that to do sensitivity analysis, as we'll discuss later, to really identify the bottlenecks quickly. And that was super useful. And we also used that eventually for a more thorough analysis on these scenarios. Lastly, the Gantt visualization was really helpful for debugging the model. So while we were developing it, we used that a lot to debug. So the simulation model, the structure is similar to any other simulation model, but we have input data that takes all of the historical production data for the corrugator, the number of piles, the characteristics of the orders that were simplified into families according to distributions, flutes, colors. You'll see what all that means very soon. Then we have the equipment production schedule, equipment cycle times, setup times, all of their parameters, and a little bit on workforce availability. And the simulation model is what contains all of the material flow, the routing rules, all of the logics behind it, the operational rules, and the logics that are specific to the equipment or to the orders, depending. And lastly, we have outputs, which are mostly the throughput, because we want to get to 2 billion. That's the ultimate objective. So we're measuring that. We're looking at equipment utilization to try and find out where the bottlenecks are, the queues. We do time state analysis to different equipment. And lastly, the floor and garage occupancy, which is like a work in progress queue. So this is what the plant looks like, or the manufacturing center. So number one here, you have the corrugator. So that's where everything starts. And then this is the exit of the corrugator. This is where our simulation begins. Piles are created here of corrugated sheets. Then this is the whole garage where you can see like this is the train, sorry, the train moves along this lane. What it does is it takes the piles from here and it drops them off at different presses to be turned into boxes. Now, if those presses are already busy, they will be placed in the garage here. All of these are lanes to store the piles while waiting for the transformation step. Some piles can also be stored here on the floor if they're too big to go in the garage. And then number 6 here is the laminator. Like we said, the fancy printer. Some orders need to go through here before they can come back this way and go into the presses. And then lastly, this is all the exiting lanes. So the orders go through here before they can be packaged this way. And lastly, they go through the shipping department through 9 here. So the simulation scope, the simulation starts after the corrugator. So we don't model the corrugator in much details. It just creates some piles, and then they are transformed, processed, and they sync pretty much at the shipping department. The shipping operations are not modeled in a lot of details either. So this is what the simulation model looks like. So we can see this is the corrugator. The piles are being created here. Some of them go through this way. That means they don't need to be transformed. But most of them are picked up by the train and dropped off at one of the presses. There's also some that are waiting in the garage. They will be moved from the garage to the press eventually by the train, as we can see now, actually. And then once they're transformed, they become little bales that move on the exit lanes to be packaged here. And then some forklifts will either place them in a truck or in the storage space at the end. So how we approached this project, the first thing we did is we did a pretty big discovery phase where we went on site. We really tried to understand all of the processes, the flow of the material, and we collected some data that we analyzed, and basically we needed to understand everything that was happening before we could design the model. Then we started designing the model, and we had a lot of design reviews. This is something we did iteratively with Christian and his colleagues to really make sure that we understood it well. And that's also when we structured and prepared all of the input data by fitting distributions and making sure that they were representative of reality. Then we started developing the model, and again, we would do that iteratively. We would develop a small part of the model, validate that we had understood well, and that the simplifications were okay, that they made sense, and that the level of detail was good enough. And then that's when we also started having outputs and having KPIs that we would compare to the real performance of the plant in the previous year, so 2024, 2025. And we would make sure that the model was precise enough and that it was reproducing the same results as the real plant. So there was a couple of iterations of that. Initially, it was maybe too simplified. It wasn't close enough to reality. So then we detailed it a little bit until we were close enough that we could use this model to test and be certain enough that it would reproduce the same behavior as the real plant. Then came the model adaptation so that we could test different scenarios. I talked about like different layout scenarios, moving some of the presses around, also removing some of the bottlenecks. But we had a huge amount of scenarios that we wanted to test, and obviously limited time and budget as just in any project. So what we did first is we did a sensitivity analysis. So and more on that later, but we basically tested if we increase the production to theoretically 2 billion or more, where was it going to block first? And then we would remove that bottleneck, continue increasing the production, and then see where it would block after. And we basically picked the scenarios that would address those bottlenecks more specifically so that we could narrow down our analysis. Then we did the scenario analysis. We compared similar scenarios to our base case scenario and found a way to explain the results and the model behavior. And lastly, we combined some improvements and did a final sensitivity analysis to have the final recommendations on the investments that would bring the capacity of the plant to 2 billion square feet. So a little bit on what supported our analysis. So initially, we collected all of the raw data that was in Excel files, and some of them were expert estimations that we turned into formulas and different things that we processed using a Python script. Then we cleaned the data and all of like we did the exploratory data analysis. We extracted the important parameters and fit the distribution using the Python script still. And then everything was ready. We created the Simio input tables directly in Simio. Like we mentioned, we developed the whole model using Simio. And then we also generated the CSV, the output data, directly in Simio. And then we, once we downloaded those CSVs, we were able to process them using, again, a Python script, because sometimes we would run some scenarios on one computer, on Akram's computer, and then I would run some others, and then we would put everything together, like aggregate and compare the scenarios using the Python script by extracting each our CSV file. Simio also has some dashboards, so we could visualize some of the outputs using those dashboards. So here we can see the time state of the train utilization. So we can see its utilization is 86%, and the details are all here. And we also created one for the garage utilization and the floor storage, so we could see it vary during the simulation time. This is a whole year. Some challenges that we had, so Christian already talked about the product mix being very large, and every order is customized to the client, so it's more than very large, it's technically infinite to the number of orders that you have. So it varies by flute type. So flute type is kind of the thickness of the corrugated sheet. The number of sheets per pile depends, the dimensions change, the color, the type of transformation that it needs, the type of packaging, and there's even more criteria that make the orders different from one another. So we're going to see next how we address that challenge. There's also the train routing logic that depends on the state of the system. So the train will bring the different orders to the press or will store it temporarily. But it really always changes, and we're going to see how we were able to simplify and modelize that. The garage is a set of 65 conveyor lanes that hold pile temporarily, like I mentioned, but it technically works last in, first out, which requires extensive planning, or you can place an order behind another and basically create a delay or block an order that needs to be produced first. And lastly, the lack of time studies for the train. So because everything is decided in real time by the operator, there was not a lot of recorded data for that. So we had to be creative in how we modeled the train. So how we address the challenge of the product mix is that we started by creating a production lot of the corrugator of the same flute type according to a pre-established schedule. So that was a number of piles that we grouped into a certain number of orders that followed a historical distribution of order sizes. Then we gave the order some characteristics like the width, the length, and the number of sheets per pile, which basically determines its height. And lastly, if it's a finished product or if it needs some transformation. Then we went to production characteristics. So if it needs a laminator, the type of press it needs, if it's going to have some cutting action or not, and the number of colors. Then there's a matrix that looks at the characteristics of the orders and the characteristics of each of the presses and determines the presses that are possible that have the capability to produce that order, basically. And then it will select only one press. And then the bale characteristics are assigned. So from that pile, how many bales will be created? Sometimes it's more than one. And then the length, width, then the packaging of that bale. So we were able to basically not have customized orders, but using the historical distribution of all of those characteristics, we were able to simplify the orders. And that was possible using all of the Simio tables. So basically here, you can see that the equipment is configured. So we have all of our machines here, their size, their capacity, the input conveyor length, and even their productions, their schedule of when they're open and when they're not open. Everything was configured using the Simio tables. And this is the press capability matrix. So each press, what flute they can produce, the number of colors, if they can do cutting or not, what type of press they are, their length, all of that was already, it was already in the input parameters. Then we have each press, depending on the flute, their cycle times. We have a distribution and we have a maximum just so the exceptions are not in there. And the same thing for the press setup. So you have each press that depends on the flute, the number of colors, the decoupe is going to determine if there's a factor or not for increasing the setup time of each press. And for the pile distributions, everything was determined depending on the flute. There was a distribution of the width that the pile would have, and then that was rounded to the nearest integer. And then depending on the width, there was a distribution of a discrete distribution on the length of the pile. And then there's other attributes. So depending on the order, depending on the flute of the order, there was different percentage of chances that it would have those characteristics. And even the number of piles per order was determined on the surface. So we would look at the surface of the orders, and you can see that larger orders tend to have less piles than larger orders, for example. So everything was linked together in a way that it would really show the same profile of the demand as reality, but it would still have the flexibility of choosing different presses. So the train routing challenge, it's not that easy as you can see here, but the first thing is that we would identify using the matrix the presses capable of producing that order. And then most of the time there was multiple presses that were capable of producing one order. We would select one press only based on an equation that the equation balances the priority of the presses, which is highly linked to their operation cost. So generally, the smallest press has the least operation cost will be priority number one. But if there's too much of a queue already at that press, there's too many orders that are already scheduled to go at that press, it might switch to the next priority. So that's how we select that one press. And then once the press is already assigned to, once the order is assigned to a press, all of the presses here have an entry conveyor, which basically holds the orders that are going to be processed next at each press. Once that conveyor has some space available, it will request the train to go get an order either in the garage, directly at the corrugator exit, on the laminator return conveyor, or at the shop floor. So the train will get from one of those sources an order to bring it to the press conveyor. And lastly, they will be processed, transformed, and then they will go to packaging. And this logic, it was a lot simplified from reality, but still flexible, and it avoids starving the presses. Lastly, the garage challenge. So everything that you can see here is technically a garage lane, and that's how it works in reality. Some piles are small enough that they only take one, some are large that they take two, and some are even larger and they take three garage lanes. And in reality, there's 65 of those lanes in the garage. And we did not want to model all of those. So what we did is that we simplified it into 15 lanes, but we maintained the total capacity. And then because the last in first out requires extensive planning, and it was a bit more complicated to model an order that would get stuck behind another, we avoided modeling that, and we just looked at historical data, and we said that, okay, well, those events of an order being stuck behind another occur about twice a week and cause a delay of about an hour and a half. So we just modeled that as an event that happens randomly twice a week in average. The train loading and unloading time was a challenge because we did not have historical data on that, and our system expert estimated that it was an equation that would depend on how deep the pile is in the garage, because the loading happens manually. You have an operator that needs to push the piles onto the train. And also based on the number of loading cycles that need to happen. So for example, if you have one big pile like that, the train has 3 conveyors, so he only needs to push this one pile and boom, it's loaded, that's it. But if you have smaller piles, you need to load each conveyor separately. So then you would have y equals 3 loading cycles. And then x would be the depth, and then the loading equation was that. So that's how we came up with the time that it would take to load the train from the garage. And similar equations were done from every single one of the sources that are here. So for example, from the garage, from the exit conveyor, from the laminator, and from the shop floor. There was an equation for each one of those. The model experiment is, as I mentioned previously, what we use the most. So this is a little bit of our sensitivity analysis. We simulated more than 100 experiments. You can see here, we started running out of numbers, so we used 993, for example. But what we tested first is we have our base case scenario. We would play with the controls to parameter the analysis that we wanted to do, and then look at the responses. What you can see here is the base case scenario. Then we started reducing the corrugator stoppage time to basically have it produce at max at infinity. And then we saw that our first bottleneck was at the train. So then we reduced the loading and unloading time of the train until that was no longer a bottleneck. We would look at its utilization. And then we started decreasing the cycle time of the presses. And then we started decreasing the setup time of the presses to create basically more capacity. And then the downtime of the presses, basically 100% is not 100% because there would be no cycle time left, but it was a percentage of realistic improvement that we could have until the transformation step was no longer a bottleneck, and then we would look at what was the next bottleneck. So that was this is what we call our sensitivity analysis, and that's what allowed us to basically narrow down all of the potential scenarios into the ones that were more interesting. And this is what the response looks like. So here we're looking at the total square footage. And this analysis was done on 2 months, and then we would do ×6 to we would extrapolate it to a yearly result in order to see if we were getting closer to the 2 billion objective or not. And we can see that scenario by scenario, it increases and then it goes back down and then it increases again. So that's how we were able to track if the bottleneck was lifted or not. So the outputs and the post-processing. So this is the function of Simio that allows us to export the details and the summaries of each scenario that we would analyze. And then using Python, we were able to generate those. So this is the percent time that each press passes processing in a failed state, starved, or blocked, for example. And then here, this is how we generated the confidence intervals of our throughput results to see if there really was a difference or not. So lastly, when we started the project, the plan had a capacity of 1.42 billion to be more precise. And the first bottleneck that we identified using the sensitivity analysis was the train. So before we could address the train, we tried some planning scenarios to see if we could optimize the lot sizes of the corrugator or have zero absence by overstaffing a little bit or a lot. And then we were able to get a little bit more than 142 by just reorganizing the planning. But obviously not to 2 billion. So then we addressed the first bottleneck being the train. So when we debottlenecked the train, we were able to get a little bit higher than this first test. And the train was successfully debottlenecked using that scenarios, which was an automation scenario. But there was a second bottleneck that was created at the presses. So then we tested continuous improvement scenarios that we call them, that were realistic improvement using probably some Kaizen strategies in setup, cycle, and downtime. And we could see that we were able to get a little bit higher than the previous scenarios, but still not to 2 billion. So then we are currently testing some investment scenarios to buy new equipment or add features to currently existing equipment. And we're hoping that we're going to get to 2 billion, but we don't have the final results yet. Scenarios are still running. And lastly, we will combine some of those scenarios that address the train with some of the scenarios that address the bottleneck at the presses. And basically the answer we are looking for is what's the combination of improvement or investments that achieve the target 2 billion square feet of throughput under a realistic corrugator with minimal investment. And that's it. Thank you for listening.
All right. A great presentation and good morning to everyone.
Good morning.
I think that was very well done, and looks like a lot of different insight went into that. And I'm seeing plenty of questions come in, and we will get started. And we can take it any which way on who wants to field which question. We can take it case by case. All right. So at the beginning, you initially identified 4 different suspected bottlenecks. What did you review to determine whether or not an operation may be a bottleneck?
I'll let Christian answer that one because he's the one who did the initial evaluation of the project.
So usually when you work in any plant environment, everybody has their thoughts and ideas of what is the problem within the plant. So we started off just with all those thoughts from all kinds of people around the plant, and we kind of had an idea what was limiting our production. Obviously, this could be wrong. It needs to be proven as a second step. So we started doing initial analysis, and then after that, we simulated. We got the sensitivity analysis, so we were in a position to confirm or not that those operations were the bottleneck. So it starts from tribal knowledge within the facility, and it goes up to the point where we're able to prove it with the tools we're building.
Excellent. Yeah, I'd say I'm sure utilization is, I feel like, a common one, but I'm sure there, like you said, there's a lot of expertise beyond that that helps to provide more theories to start things out. Let's get the next one here. So what were some of the modeling challenges of having to consider a unique product mix versus a fixed set of product SKUs?
So as we mentioned, we did have a large variety of products. Everything is customized to every single customer. So the way we dealt with that is we focused on some key characteristics of the demand, like the number of colors, for example, the type of corrugation, and the sizes of the orders. And we kind of made categories with that, and we generated a bunch of orders based on the historical distribution of those characteristics. And then we had a dynamic decision that would look at the characteristics of the orders and the characteristics of the presses to route the orders to the right press.
Okay. Yeah, I would say I'm sure with that in mind, there's characteristics that are important to consider for other operations, but what does that matter for specifically for operational analysis? What are those conditions and how do they consider? Good stuff. All right. Similar along the lines of decision making, what goes into the decision of making your entity and the system represent an individual corrugated sheet versus a pile? And I know in case I'll add on, you said orders. So it sounds like it could have been many different things depending on how you interpreted it.
Yeah, so we actually considered it at first having a corrugated sheet as one of our entities, but we wanted to keep the model as simple as possible, and we wanted it to run as fast as possible. And so we ended up making the piles the entities, but the number of sheets are a characteristic of that pile, because depending on the size of the pile, we can have different heights. That is something that is regulated. So the number of sheets ends up being a characteristic of the pile, and then the number of sheets ends up determining the transformation time at the press, because the cycle time is usually per sheet.
Okay. Yeah, I would say I feel like that's a kind of a conceptual modeling challenge of do we have an entity per sheet? Obviously, you'd have a significant number of those versus can an attribute capture the behavior we're needing? So I think that's a very common challenge of establishing that up front.
Yeah.
All right. Let's see. So how much of the development of the routing and operational rules came from your experience versus what may work well versus inputs that you received from Mitchel Lincoln?
So a lot of the routing logic came from Mitchel Lincoln, right? We mentioned in the beginning, we visited the plant, we looked at how they route everything. And then the operational logics, that came from a bit of both. So understanding how things happen in real life and our experience to basically simplify those logics so that the model can run efficiently and so that we can stay also within the budget that we're allowed for the project. And then we try to basically find that right balance between having a model that works like the original system and also keeping it simple and within the budget. And an example I can give for that is, for example, the garage logic. In real life, it's last in, first out. We simplified that in the model by having it first in, first out.
Got it. Yeah, I would say I think that the big thing there is just kind of like you said, consistent communication with the stakeholders of how we're interpreting this for simulation purposes, and here's that real life translation, and striking the balance between the two.
Yeah.
Similar. We're getting a lot of things one after another that are similar to one another. is your priority index for selecting a press something that is proprietary to Simwell, or maybe that's a part of, you developed that with the project?
So it's not something that is like a strict rule in real life, whereas we have it as something that is like definitely that's how it works in the model. So we spoke a little bit with Christian, and it's kind of like intuitive. So the way the train works in real life is that there's an operator, a human operator on it. And so that's kind of an intuitive way that he works, but it's not like a very strict rule that he has to respect and to stick to. I don't know if you want to add something about that.
I'll add something to that. Right now, I mean, we are using a human decision to determine what goes where, and we're wondering if there's potential optimization available here, or a capacity improvement if we were to use an algorithm, for example. So this is one of the potential future phases that we could explore. First, demonstrate that if the decision would be optimal, what capacity we would gain, and how much would it cost to build this algorithm. Instead of buying brick and mortar or new equipment, we could go down the algorithm path to potentially increase the plant capacity.
So this actually ties in. There was another question about, did we consider optimization or not? Well, right now we didn't, but it could be a potential expansion to this project.
Yeah, and I feel like that is another challenge of the capturing the experience of the shop floor into the model of how does your 30-year veteran handle the procedures of determining what goes when, and having a model that represents that. Obviously, that's experience that you can't difficult to replicate otherwise, but very important to get the accuracy of that model.
Right.
So I think this was right after you mentioned the train as a bottleneck. Can you talk a little bit about the lot sizing exercise you performed?
Yeah, so this was really interesting, right? So we kind of kept in mind the lean manufacturing things about like having different lot sizes and producing the products at a certain interval, right? The famous every product, every interval from lean. So the idea was that we wanted to see if there was an impact on the lot sizing at the corrugator and the starve time on the presses. So when you have really large lot sizes, some presses don't produce a certain type of corrugated sheets, and so you can have some times where some of those presses are starved because you have a very big lot size at the corrugator. So we tried different experiments where we played with different types of corrugated sheets, the different flutes, and the lot sizes for each of those. And we wanted to see the impact on the utilization of the train and on the also on the starve time of the presses. And it was really interesting. It didn't show huge results, but we were able to tell that it would make a small difference for sure.
And I guess along those lines, just for my curiosity, would a lot size consist of multiple orders, or would you do order splitting, or it could maybe all of the above?
Yeah, so a lot size is multiple orders. Each order can be multiple piles. An order can be very small, like 2-3 piles, but it can be very large, like 60 piles almost. And so, yeah, a lot size would be multiple piles, so multiple orders.
Interesting. Yeah, I was saying that's lots to consider there, especially given all the uniqueness of each product and what needs to get bundled together and things like that.
Yeah.
Let's see. Still plenty of questions coming through the hopper. All right. So was the train still a bottleneck prior to the purchase of the new corrugator, or did that pop up after the fact?
I'm gonna let Christian answer that one.
So the train and the corrugator prior to the investment were pretty much head to head in terms of being the bottleneck. The reason for replacing the corrugator was for future expansion, and also the section we replaced was end of life. So we had to replace that section, and those types of machine will typically run for 25 years. So we knew we were going to go through an expansion, so we had to get the extra capacity when we did that capital project. And we knew for a fact that the train was going to be the bottleneck afterward, but from the tribal knowledge. So it's just that we utilize less hours in a week to operate, knowing that the new corrugator has more capacity now, but we're going to utilize it in the future years to come if we improve the different bottlenecks that we have that remain within the plant.
Yeah, I was saying, in the world of packaging and parcels, there's going to be packages for a long time to come.
We should be good to go.
Let's see. So, did the physical size of each order impact the amount of whip space you had available?
For sure. Well, the bigger the order, the more space it would take in the space that was available for the work in progress, right? So if we have an order that has something like 60 piles, it definitely takes more space in the work in progress storage. Yeah.
That makes sense. Let's see. All right. So I think pretty similar to that lot sizing we mentioned, did all piles within an order have to be processed consecutively, or could you work on portions at a time?
Yeah, consecutively, because we want to have only one setup time to do. So the setup time is on the first pile of that order, and then the press kind of like stays busy with all of the piles of that order before it becomes available again for the next order.
Okay, so each order would be unique enough that it would warrant its own setup. Okay.
In this industry, there's no standard products. So we don't do long run of something. Every customer has their products, and for each of their products, they have a specific box. So everything is made custom, and the machines are pretty flexible, but every order requires a setup for the specific customer we're going to be producing.
So a setup for the number of colors, for the printing pattern, and a setup for the cutting pattern also, right?
That all makes sense. Let's see here. So can some of the throughput shortage from the desired 2 billion square feet be due to product loss during operations like box punching?
Not really, because the way we calculate the throughput comes from not what comes outside of the press, but what goes inside of the press. So actually, if we consider something like 2 billion square feet, it's what was inputted into the presses plus what is sold as a final product as a corrugated sheet. So no, not really.
Obviously, there's waste within the process, but it's a few point of percentages that randomly happen. So it's not the main reason for not being able to process.
Okay. Yeah, I was saying, sure. In a lot of industries, those are byproducts and waste that has to be accounted for in some aspect. But like you said, well accounted for in this case.
Yeah.
So does your customer use the final Simio model to run their own scenarios, or are you delivering them the results and recommendations yourselves?
So it's a little bit tricky here because we don't have an operational model yet, right? We're not in a scenario where we're making decisions on the operations day to day. We're kind of evaluating, like we said, we have a little bit of an increased capacity at the corrugator, which is something recent, and we're trying to find a solution for the rest of the plant to be able to follow. So it's kind of more of a one-time analysis. So because it's not an operational model, it was less applicable, but it is still a discussion that we had, right?
Yep.
So if you want to add to this.
Right. If we get to the critical mass to have enough decisions to be made, of course, we could look at getting a license ourselves, but at this point in time, with it being a one-shot deal for now, it's not something we consider.
Yeah, I guess the timeline for some of your decisions, you're not going to go and immediately react to some of the results. There's some planning and execution that goes into that versus if you're running a model to say, what should we work on our shift today? So you're more reactionary to those. So that makes a world of sense.
But yes, and also what I can say is, let's say we determine an asset is 20% undersized. We may have a list of 2, 3, 4 solutions to gain that 20%. So now we know the number. So now we have to find what is the best solution to address the number, but we know the number. So not all the designs of all solution to debottleneck the different assets have been completed. So there's engineering work that will need to happen from now on to really fix the plant for us to be able to attain our 2 billion square feet.
Makes sense. So we have a few more here. So did you do any sensitivity analysis regarding the effects of adding another train, or is that not feasible to consider?
So it's not one of the scenarios that we tested. It was not one of the scenarios of interest. Is there a specific reason for that?
Those systems exist, but I find them pretty inefficient. It's not because you had a second train that you gain, you double the capacity, because there's lots of interaction between those trains. They always bump into each other, and sometimes they have to drop the stock, and then the next one takes the stock, and then it's going to bring it to the other one. So lots of those interactions make it inefficient. The other way to do it is a two-stage storage area where you have one train on one track, then you have conveyors in between, and another train on the other track. These are pretty pricey. But as I said, we didn't get into the design yet. So where we're at right now is just to know how much more capacity do I need for the train. So if my answer is 10%, I have non-capital options, I have capital options. I could speed up the train, I can add another train, I can motorize conveyors, I can automate conveyors. So the list of options right now is quite long. What I need to know is how much capacity do I need to gain on the train in order for this not to be a bottleneck and prevent me from getting to my production capacity that I look for.
Makes sense. Just as you said there, there's a wealth of scenarios you could run prior to determining what actions may be needed for that.
Yep.
Mm-hmm.
All right. So was there any optimization involved? And I think you already answered this, that it's an opportunity, but around train utilization, maybe it sounds like that's another possibility for optimization down the road.
Yeah. So currently, no. It's a potential expansion. We're gonna see if it's worth going there or not. But right now, it hasn't been decided whether we're gonna do that for sure or not.
Sounds good. All right. So this is looks like this is around the lines of kind of assumptions and validation, but if you don't model the full 65 lanes, how do you explore if you can gain efficiency by adding more lanes?
So the lanes of the garage are modeled, we talked about, we modeled 15 lanes, but we have the same total capacity, right? So we have the capacity of the garage is maintained. And actually, we're not trying to determine how much it would help the train by just having more inventory. There's already a lot of work in progress in some of the scenarios. And what we're trying to see is more like the efficiency of the garage, the efficiency of the transformation press. Having more inventory, more work in progress is not necessarily something that we want to evaluate if it's going to help. Actually, we want to reduce the inventory by not having any bottlenecks, right? We don't want to build up of inventory in between the processing steps.
If I can add that, there is also the capacity of the garage that we can change on the model. Even though we simplified it to 15 lanes, the capacity can be changed in the model so that we can test scenarios where we have more capacity of the garage, so more lanes in real life.
Yeah, and I'm saying that goes back to some of the modeling decisions you make of what is the practical output we're getting versus how are we going to model that, and without having to overcomplicate matters unnecessarily. So sounds like a lot of those are well considered. Looks like we have one more here. Was some kind of a peak week analysis being done? So during the holiday season, maybe more purchases, typical. And what was the time frame of this analysis?
No, so we didn't do that. We modeled on a horizon of a whole year. We did have some holidays, but we kept the historical pattern of the demand, but we didn't necessarily have a lot of seasonality in the model. We didn't test like some specific periods of time. We wanted to look at it from a yearly production capacity, and that's what we focused on in the analysis.
And the reason being that this industry is not very seasonal in general. Some markets could be. Obviously, if you're close to big growers or stuff like that, maybe your book of business could be more seasonal, but this plan does not see huge variation within the year, so there was not a big interest to do so.
That all makes sense. Well, looks like we are went through plenty of questions. Appreciate all the perspective and the insight there. And I want to thank you all for your participation here at Simio Sync. Great presentation. I think a lot of great industry insights. And looking forward to the presentations that follow. But any other closing thoughts?
I think that's it. We covered a lot. Thank you for your questions. It was really fun to have this much participation. And that's it.
Excellent. Well, again, thank you all, and looks like we've got more videos to come.